So there's a lot of misnomers out there. Roman statue, have you ever heard of that? No. Okay. So the next force, then, that was weight. Now let's do normal force. Let's see. Normal force. And you're going to think, I learned normal force in high school. How could he possibly complicate and make normal force confusing? Here we go. Okay, here we go. So the normal force. All right. When you push something, it pushes back. That's really all it is. Normal force. So take your hand like this and push it with your finger like that, right? I mostly just want to watch you do this. It's funny to me, right? But if you do that, you're pushing your hand, and your hand goes, oh, I felt it. Oh my God, stop, right? Your hand feels this big force, but now think about your finger. Oh, you feel a force on your finger too, don't you? There's no way to push your hand without feeling a force on your finger. Okay, there is, but with your finger, there's no way to push your hand without feeling a force on your finger. So whenever any two things push on each other, they both feel a force. They both feel the same force. Right? So that's the normal force. So really, it's sometimes called a contact force. Okay? We're just going to use the word normal force for all the occurrences, no matter what direction it is. Anytime two things push on each other, we'll call it a normal force, and we'll use a little n, because that's what the book uses, little n. Okay? So let's think about this. It's a vector. All forces are vectors. And the first thing we think about is the direction and the magnitude. Right? The direction of the normal force is perpendicular to the surface that creates it. And you could say, isn't that arbitrary? No. Any two surfaces in contact at a teeny point is making a line. It has a direction. Even if I have a round thing touching a flat thing, at some little point, microscopic point, it's an area. Right? It has a direction. If I have a perfectly round object hitting a perfectly flat object, then the normal force is this way. So there's always a direction perpendicular to the surface where the two things interact. Because if you want to get specific, they interact at just a point. There's even a direction at just a point. Okay? What is the magnitude of a normal force? Okay? It's not very mathematical. Whatever it takes. Whatever it takes. However much I have to scream up here to teach you physics, it will happen. I'm like a normal force. Okay? Whatever it takes. So let's see. Let's think about a normal force here. Here we go. Here's a block sitting on a table like that. And let's draw that. Let's see. So here's the table like this. And this little marks here mean it's a solid table. It's not going anywhere. And here is the block sitting on the table. It's a block with mass m. Yeah. So let's see. Let's draw some forces on here. Let's draw the weight. Oh, the weight acts at the center of mass. Center of mass is at the center. All right. Now let's draw the normal force. And you say, okay, well, the normal force, let's see, the table must be pushing up on the block like that. But wait, he also said the block pushes down on the table like that. Well, those are two normal forces in opposite directions. Now I'm confused. I don't know. What happened, right? So this is what we want to think about using a free body diagram. Right? So this is this, direction, magnitude. And now on the side, we'll use our normal force and our gravitational weight to think about use a free body diagram. Free. I'm not even going to write it out. Free body diagram. The forces on one object. Because two things got confusing when we tried to do this. One is we need some better notation to talk about who is pushing on whom, and it's get messy. It's messy here, right? It's messy. I don't like it. So right now, every object we're drawing and thinking about, we're actually treating as a point mass. Okay? We're not actually considering that it has a size and a shape. We'll think about that when we get to rotation. But for now, it's a point mass. So if I were going to draw a free body diagram of the block, I would put something there. These poor poli-sci grad students have to listen to me shout for 70 minutes. I would put just a point and say, there's the block, right? That's it. And then it's easy. You put all the vectors on the block. So here's weight. Oh, it lost weight. And then where do you draw the normal force? Also just draw on the point, like that. Normal force. And then use subscripts to help you keep up with which normal force you're talking about. So usually the first one is what's doing the pushing, and the second one is what's receiving the pushing. So I would call this the T-B. That's the normal force of the table on the block. This one down here was the normal force of the block on the table. But we're not putting that on here because that's on the table, right? This is the free body diagram for the block, right? So there it is, your first free body diagram. Isn't that more clear than this? Don't you want to do this? Okay. So it's hard to get people to do free body diagrams because you can figure it out from here. But sometimes when things get confusing and you get an angle and more components, you need to do them. Okay, so do them if you need them. We strongly recommend them. All right. Let's see. And sometimes people wonder, let's see. Oh, yeah. So now let's apply Newton's first law to get the magnitude. Apply N1 is what I call it. N1, N2, and N3. Okay? N1, N2, and N3. N1 said if that thing's not moving, and it's not moving, then the net force must be 0. The net force means you add the forces. So let's just add these two vectors and say it must be 0. The normal force of the table on the block plus the weight equals 0. There we go. That's it. I wrote them in vector form, right? So let's solve for the normal force of the table on the block. It's equal to the minus of the weight vector. That's all you need to know. Because now we know what it is. It's the opposite of this, right? So mathematically, there's not much to this. You can say, well, then the magnitude of the normal force of the table on the block is what we care about. It's equal to mg, because that's what the magnitude of the weight is equal to, right? And the direction is the opposite negative of weight, so it's up. So there's your normal force. We calculated it. And what was the magnitude? Whatever it takes. Whatever it takes to make Newton's laws true is what the magnitude will be. And you say, how can it do that, right? The table is not sentient, right? The table isn't watching me. Well, it kind of is, right? The table's not watching what I'm doing. So right now the table's applying a normal force equal to the weight. What if I push down on it? Right? If I push on it with my finger, oh, then there's a normal force between my finger and the mass, and then there's another force pushing down. We would put it here, and then the normal force pushing up would have to be my weight plus the finger magnitude. We'll do the details in a minute, right? So if I push down, the normal force went up. Then I release it, the normal force went back down. Right? I push it down, I release it. How does it know? How can it figure it out? It's so smart, right? Basically, if you want to try to get an intuition for normal forces, is just realize that when I do that, I'm deforming the table, okay? And the table acts like a really stiff spring. So just think of everything you touch. All solid objects are stiff springs when you push them together. Even if they appear rigid, they're really stiff, right? That's deflecting probably quite a bit. It's a 100-year-old table, okay? So that's how normal forces work. That's why they can take whatever value it takes. Why is there normal force going down on the block? No, I didn't mean to draw it down. Yeah, because you didn't do a free body diagram. There's no normal force going down on the block. That's the normal force of the block on the table. That's why we draw the free body diagram, is you saw something on the table and thought it was the block. Thank you for illustrating my point so perfectly. I planted that. Dr. Stenson texted that one in.